Morning, class. Thank you very much for the very kind introduction, Brevin. It's an absolute pleasure to be here. This is my umpteenth GOTO event, which I'm always delighted to be invited to. They're some of the, well, probably my favourite conference events, or conferences in the world, actually. So thank you very much for the invite. As was mentioned, I'm going to be talking about, I guess you could call it the sort of the craftsmanship of how we build teams, and how we build organizations, and how it relates to software architecture, and how it relates to the structure and the shape of teams, of the teams that we build. Just make sure this is turned on. It is. First, I did want to mention something that's a little bit sadder, though. I'm not going to dwell too much on this, but I did want to acknowledge Stefan Tilkov, who many of us in the GOTO community knew very, very well, and who sadly passed away very recently. So Stefan, if you don't know Stefan, he was, I guess, one of the founders of the microservices movement. He sort of came up with the idea of self-contained systems. Previous to that, I knew him back in 2005-06 as just a guru about all things REST and service-oriented architecture-wise. But more than that, he was a really fun person to be around. He was a wonderful guy. And yeah, we'll miss him. So, and that's Stefan walking off into the distance on a beach in Anguilla, which is probably a nice way to remember him, to be honest. Yeah, but I'm going to move on from that because that's not what we're here to talk about. Obviously, we're here to talk about software architecture, team topologies, and complexity science. Now, back in 2014 or so, I'm going to step back here, so I can actually see the screen, this one. Back in 2014, Martin Fowler and myself wrote what sort of became the canonical definition of microservices. And in that we said, we cannot say there's a formal definition of the microservices architectural style. And then we went on to list a number of characteristics that we were seeing teams use in the wild. I mean, this is going back a long, long time now, nearly 10 years, which is a long time in software engineering terms. I mean, Kafka wasn't around, Docker wasn't around, Kubernetes was a glint in someone's eye, 10 years ago. And these were the sort of the core characteristics that we were seeing teams using and being successful in the wild, essentially. And over the last sort of decade or so, I've been sort of deeply thinking about why these things work and why they still work. I know there's you can talk about some controversy around things like moving back towards modular monoliths and whether AWS actually moved away from microservices or not. It's not in that case. But I've been thinking quite deeply about why this stuff works. In particular, I've been thinking about some of the sort of characteristics that relate to decentralization, if you like. So there's a number of things here around things like organized around business capabilities, products not projects, decentralized government, there's decentralized data management, componentization via services. It seems to be a theme that's running through these running through microservices and the adoption of microservices is pushing decisions down to the point with the most information, so not retaining decision-making in some form of hierarchy, but pushing decision-making down, ensuring teams are autonomous, cross-functional, these sorts of things, running them as long-lived product teams generally, and decentralizing governance and data and so on. And so this talk really is about what I've been thinking about over the last 10 years, and my sort of the current state of my head when it comes to software architecture, how we build things in the large, how we build organizations in the large, and how we can use sort of more interesting research from the last, decade or so to help us when we do that. So first of all, I'm going to talk a bit about team topologies and complexity. So I was at an event, actually, in Anguilla, funnily enough, and someone at that event, who was from Amazon, they said, at Amazon, the bigger we get, the easier it is for us to get bigger. The bigger we get, the easier it is for us to get bigger. The more products we build, the easier it is for us to build more products. The more people we add, the easier it is to add more people. The more teams we create, the easier it is to create more teams. Now, I appreciate these are very comfortable chairs, and it's very early in the morning, relatively early in the morning, but you put your hand up if this is your experience of working in an environment building software. Okay, so that's the Amazon people with their hands up. So there are a number of you in the room, which is awesome, right? But the vast majority of people in the room aren't feeling this resonates. They're not feeling that this is the general sort of way we experience life writing software or building teams or running teams. Now, I like this quote. What's the purpose of building teams? What's the purpose of what we're doing when we form a team and when we're delivering software? So Daniel Tuhorst North is going to be around, I think, later today and certainly tomorrow and I believe Wednesday. And he says the purpose of a team is to safely and sustainably reduce the lead time to thank you. Right? That's the purpose of what we do when we build a team delivering software. We're trying to reduce the lead time, not just to being in production, but further than that, to someone actually using the product that we're building and saying thank you for using the product. That's the sort of purpose of putting teams together. So how do we build teams that allow us to go as fast as we can, essentially, and allow us to safely and sustainably reduce the lead time to value? But what is value, actually? And I've been thinking quite a lot about value and how value relates to what we do and how value relates to the rest of the world, in fact. Because we tend to think in what we do as knowledge workers, software craft people, however we define ourselves, programmers, developers, software engineers, we tend to think of us as special, right? We do these special things. We do special stuff, right? We take these like very nebulous ideas and we do smart stuff with code, and then we put that code into production, and then it creates value. And maybe that value is money or whatever it is. Or maybe it's saving lives, or whatever. But actually value is similar across most industries, right? The way we go about building stuff, the way we go about creating value is by taking something that's less valuable, an orange on a tree in Seville, and making it more valuable by pushing it through a supply chain and ending up in a store where we can buy it, where it has a monetary value, right? That's adding value. Or if you're a lawyer, by creating, when you take a brief, right, you add information to that brief using your expertise, and you turn it into a case, and then you prosecute the case, and so on, or defend the case. Something that has more value. Essentially what we're doing is pushing stuff through a series of steps until hopefully someone says thank you. So I look at what we do essentially as the same as what we do in actually in things like supply chains or whatever. We're moving requirements through a software delivery supply chain until we get someone hopefully to say thank you. And optimizing how we do that, optimizing the movement of this stuff is really what I've been thinking about the last sort of 10 years. We're taking essentially raw materials, passing these things through a series of steps where we add more value, whether it's a business case, it turns into epics, those epics turn into stories, stories turn into code, and the code turns into tested code, and then it's deployed, and now we're earning money. Or we're moving bananas from wherever bananas are grown through into supermarkets and so on. Which brings me to the question, and I'm a consultant, I've worked in many, many organizations across many, many industries. How long should it take to move this stuff through these supply chains? How long should we expect things to take? How long should the software delivery process last? How long should our customers expect to wait for requirements to be implemented and delivered so they can say thank you? This is a value stream map from an actual client of ours that I worked with a number of years ago. And this value stream map starts up here. If you haven't come across value stream maps, it's an incredibly useful tool for visualizing the system of work, your system of work. At this end of the value stream map, we've got things like business cases being created, options, solution architecture and options and all this sort of stuff is up here. Then we've got this group in the middle. These are two different types of data engineers and data architects, each of which have got their own canonical model of the data for the enterprise, and they just go around in circles updating their canonical models. I don't think they got the memo about what canonical actually means. When you have two of them, they don't tend to be canonical. Down here is testing. All this stuff is testing, integration testing, performance testing, regression testing, a whole bunch of testing stuff, and I'm hoping this is going to work. Can't really see, hopefully you can see that laser, but that blue sticky there is writing code. Of that whole process, that blue sticky is the bit where actually ideas are turned into executable code and run somewhere. So, this takes, well, I mean, just a bit in the middle takes about 8 days, but this was probably about an 18-month process, end to end, to go from idea through into production. But if you looked at how hard the developers were working, they were just churning stuff out all the time. Every couple of days, they were implementing something new. Then they'd have to wait 6 months or more until it actually hit production. So how long does stuff generally take? And in my experience, it takes a fair amount of time in most big organizations to get stuff done. And I refer you back to this idea from AWS is the bigger we get, the faster we go, as opposed to the bigger we get, the longer our processes get, and the more difficult it is to do anything. Which brings me to the first sort of thing I want to cover, really, which is this idea of team topologies. Now, another hands up. Who in the room has read team topologies? Who's heard of team topologies? More, and actually not the same people, which is interesting. Not sure what you were reading. So team topologies, I think, is it was published a couple of years ago now by Matt Skelton, Manuel Pais, who have been sort of stalwarts of the London continuous delivery community for many years. I've known them for many years, running user groups and meetups and so on. And they've taken a lot of thinking about a lot of thinking that sort of starts with pre-microservices and how to structure teams for success. And they've sort of distilled it into what I honestly think has become like immediate canon. Like, this is one of the most important books I think that's been written probably in the last decade about the large-scale structure of what we do, how to form teams, how to create effective organizational designs that lets us reduce the lead time to thank you. More importantly, what they've given us in this book is to use a DDD term, ubiquitous language that we can use between ourselves to describe different team structures, so that we can sort of communicate more effectively, much like the pattern movement tried to do, or is still doing, in terms of patterns for software development. It gives us a shortcut by which we can talk to each other about difficult and quite complex problems. And in team topologies, they call out 4, I'm not going to go into too much detail, this isn't just about team topologies, but they go into a lot of detail about different team structures. In particular, they call out specifically four different team structures. One is a stream-aligned team, so value stream-aligned, a long-lived team, potentially long-lived team, that's aligned to delivering value to some set of customers or other. They talk about enabling teams. So enabling teams are, there's the sort of, I guess I'd like to think of it as the sort of the teams composed of the rarer skill sets, maybe. So maybe it's your InfoSec people, maybe it's your infrastructure engineers who you don't have enough of to embed into every single team, but are essentially there to make the rest of the organization go faster and the rest of the teams go faster. You then have like complicated subsystem teams. Sometimes you have stuff that's really, really hard and only a few people know about. Complicated subsystem team. And platform teams, which obviously Liz is talking about. Platform engineering teams who build software themselves in order to make the other teams go faster at what they do, be better at what they do. And so using these sort of these team structures, we can start to see how organizations can be designed around using things like Conway's law and so on. I'll now move on briefly to software architecture and complexity. So I'm calling it the curious case of Amazon, this idea that the bigger we get, the faster we go. Now, if this is sparkling water, this could be entertaining, because it'll probably go everywhere. Tension is, it's fine, good. So the curious case of Amazon, why is it that Amazon are able to go faster the bigger they get? And is that actually true, or is that some random quote that I've just made up? Well, this is me, again, in the Caribbean, with Adrian Cockcroft, formerly Netflix, then AWS. Now he's actually sort of pretty much in semi-retirement. And this next to him, Adrian's in the middle, this next to him, ladies and gentlemen, is Melvin Conway. He's a real person. He actually exists, Mel. And I was very lucky to be at an event with the two of these folks and some people who were at this event, actually. And we were talking about the uses we've put Conway's Law to over the years. So Conway's Law, for those of you who haven't come across it, it's become ubiquitous. Conway's Law essentially says that the structure of your organization is going to influence the structure of your software architecture. So the way you design your organization, or the way your teams look, that's how your software architecture in the large will look over time. It's also known as the mirroring hypothesis. Your software architecture will mirror the structure of your organization. And this was written in the late 60s. So we were talking about the uses we put this idea to. Adrian was talking about how at Netflix they would sit the people who need to talk to each other the most next to one another. So the UX teams would sit next to the platform team, not the API platform team. They wouldn't sit anywhere near the Cassandra teams. They didn't need to speak or talk to the Cassandra folk very much, but they did need to talk to the people building the APIs they were using. So, sitting people close together so you have the highest bandwidth between those groups that you can. And Mel was just freaked out by this. He's like, I can't believe, these giant organizations are using this little paper I wrote, 50 years ago now, to actually design them, design how they operate. But at this event, again, as I said, this quote, someone at the event said this. Tie myself in knots there. But of course, if you've done any research into the history of team structures, project management, and so on, you will have come across the mythical man month, the late great Fred Brooks, who in that says, actually no silver bullet, adding manpower to a late software project makes it later, right? This is received wisdom in our industry. As we get bigger, things get slower in general, and you can't solve a late project by adding more people, because at a certain point, the productivity of the people you're adding is overtaken by the complexity of the communication and the increased communication overhead of adding those people. And this is sort of received wisdom. So what is it about AWS that's sort of flying in the face? And is it, in fact, flying in the face of this? Well, this is from a few years ago, warning pseudograph, sorry for the data people in the room. But I plotted revenue versus employee count for Amazon over a number of years, and this is publicly available information. Andy Jassy showed a very similar graph at last year's reInvent, I think it was. But the key thing here is this exponent of 1.15. What this means is, on a log-log graph like this, what this means is that Amazon is growing faster than it should, essentially. As they double their revenue, AWS doubles revenue, they more than double the number of employees. We'll put it the other way. As they add more people, as they double the number of people, they more than double the amount of revenue they're taking. Right, this by 115% effectively, 1.15. This is something called returns to scale. As they add more people, they get faster. As they add more people, they make more money. And you'd think that would be the case for most organizations, but it's not, and I'll come to that now. So why is it that Amazon are able to do this? Well, back in 2004, there was this famous memo from Jeff Bezos where he used what I like to call this idea of forcing functions for flow. How are we going to migrate away from our sort of traditional, monolithic, Oracle-based back-end software architecture towards the SOA, or it was the many redundant words were going to be used then, the service-oriented architecture that they adopted based around something that looks a bit like microservices, but not quite. So one of the things was teams must communicate via interfaces. We can no longer sort of fertile with each other's databases, talk database to database. Everything has to be through an interface. The next thing was that these interfaces must be externalizable. We must be able to essentially sell these things. They must be robust enough that we can present these to the outside world. And this was not just for the software services, but also for the infrastructure services. And then finally, the famous two-pizza teams. Now, the combination of all these different things have led to this incredibly sort of decoupled and cohesive set of team structures where they're communicating only via very, very clearly defined interfaces. And they're smallish, not that small really, but smallish, and are able to produce software that can be externally presented and sold. Now, if you think about where AWS came from, that's essentially AWS. AWS is then monetizing this set of forcing functions. Oh, suddenly we've got this set of infrastructure our teams are using to stand stuff up. We can actually start selling that. But there's another crucial forcing function, which is the idea that every team has a direct line of sight to their customer. So this is relating back to this idea of value stream aligned teams, the idea that you should have teams that have a direct line of sight to someone who can say thank you to you. It's not enough to have a team that's producing software that goes into the void that other teams might be using. You need to know exactly who the customers are and be producing software for them. As I say, I like to think of these as forcing functions for flow. So limiting interaction to nearby teams, team isolation, and scaling via something called Dunbar's number, which we'll come to in a minute. So going back to team topologies, you have this idea of a streamlined team with a direct line of sight to your customers. You have these enabling teams, you have platform teams who are providing self-service access to infrastructure that you can use to help you go faster, and then complicated subsystem teams. As a brief overview, some team topology stuff, how software architecture relates to team topologies, and how you can use these forcing functions or ideas, principles that you can put in place to guide the evolution of an organization in a particular direction, which is essentially what happened with that memo. These forcing functions propelled AWS and Amazon in the direction of these smallish decoupled, cohesive teams that they can basically just plonk more of in. So AWS, they can just create new teams, build new product, create new team, build new product, create new team, build new product. Okay, reductio ad absurdum. It's not as easy as that, spoiler, but for the purpose of this presentation. The next thing I want to talk about, because this is really about why, underneath all this, why or how this stuff works. Why is it that Amazon are able to outperform most of their competitors in terms of revenue per employee count? What's their secret sauce? Is there something that we can learn from underlying principles relating to this? And I think there is. So this idea of complex adaptive systems, which I'm fascinated by, and I hope people in the room will go off and read about because they are fascinating. Complex adaptive systems were the idea of them was created at the Santa Fe Institute in New Mexico. So this is an institute set up by a cross-disciplinary group of scientists, biologists, economists, physicists, mathematicians, chemists, a lot of whom came from Los Alamos and then brought collaborators in, to study something called complexity science. This is post-chaos theory. After chaos theory comes this idea of complexity science, and specifically the study of something called complex adaptive systems. So what are complex adaptive systems? Complex adaptive systems are everywhere. We are a complex adaptive system. The company we work in is a complex adaptive system. The team we're in is a complex adaptive system. The city we live in is a complex adaptive system. And these complex adaptive systems display some interesting regular behavior. So this is from the book, well, it's actually from this paper, but it's also summarized in the book Scale by Geoffrey West. So essentially what this is showing is a plot of body mass for mammals versus calorific intake, essentially. Right? So, well, actually basal metabolic rate, which is an approximation of that. So essentially, as you double the size of an animal, you would expect, because as you double the size of something by volume, you get a lot more cells, right, to feed, to take calories in to support. You'd expect, as you double the size of an animal, that they'd need lots more calories. Actually, that's not the case. As you double the size of an animal, so you go from a cat to a dog, or a dog to a dog that's twice as big, they don't need more than double the amount of food. Actually, they need much less than you think. They only need 75% of the calories that you would expect as you double the size of an animal. And that is true for all mammals, including us. There are some other interesting similarities between mammals. Did you know that we all share the same blood pressure? All mammals have about the same blood pressure, 90 over 140 over 90, whatever it is. Also, the Kleibert's law. Anyone come across Kleibert's law? Why would you have come across Kleibert's law? I'm talking about biology to a bunch of software engineers. Kleibert's law is this idea, well, it's not, Kleibert's law states that all mammals share approximately the same number of heartbeats in their lifetime. Right? But what changes as you double the size of an animal is their metabolic rate. As you go from a mouse to something that's twice as big as a mouse, whatever that is, and as you scale up, they get slower. Mammals get slower. They process the calories much more slowly. Their metabolic rate basically drops. So as you double the size of a mammal, you don't have to have double the amount of calories because their metabolic rate adjusts so that that's not the case. Essentially, mice run around super, super fast, live for about 1.5 years, or whatever it is, 2.5 years. Elephants, not so much. big, ponderous, live for ages. Elephants, in fact, don't get cancer, pretty much. Their cells don't divide enough in general, actually, to cause cancers. Their metabolic rate is so slow. Same with blue whales. So metabolic rates in mammals, they follow this scaling law with an exponent of 3/4. So as you double in size, as your mammal doubles in size, it only needs about 75% of the calories that you think it might, you think it should. There's another type of, as I mentioned, complex adaptive system called organisations, companies, mom and pop stores versus Aldi. If you look at revenue versus employee count from the NASDAQ over a number of years, what you find is as you double the size of a company, revenue doesn't double. You don't double. In fact, revenue scales in the same way that mammals scale. Revenue scales with this exponent of 0.85. As a company doubles in size, rather than get double the amount of revenue, you only get 85% of that amount. I refer you back to the Amazon point, where Amazon is getting 115% of the revenue as they double in size. Cities, another type of complex adaptive system. So as you double the size of a city, you'd expect you'd have to double the number of petrol stations or water pipes or sewage pipes or whatever it is, but you don't. As you double the size of a city, you only need about 85% of the infrastructure, the physical infrastructure in the city. So actually this is why cities, one of the reasons why cities are so successful, because as the bigger they are, the cheaper they are, essentially, or the more effective, the more cost-effective they are. And this is true for road length, petrol stations, number of restaurants, water pipes, and electricity cables. So what I've shown you is a disparate set of things, like mammals, people, companies, and cities, all examples of complex adaptive systems, and all exhibiting this idea of what's called sublinear scaling, or sublinear scaling. And these are the numbers. Now, in this book, I really like this quote. Geoffrey West, he talked in the book Scale, he talks about when you, basically to paraphrase this, when you see straight lines on a graph, if you're paying attention, that should tell you something. It should tell you that there's probably some underlying principles that are causing those straight lines to appear everywhere. Quantities that do not change when other parameters of the system change, they play a special role in science, he says. And what these straight lines demonstrate is something called sublinear scaling or economies of scale. So as x doubles, y increases by less than double, as opposed to linear scaling, where x doubles, y also doubles. And this is all related to complex adaptive systems and how complex adaptive systems work. So what are complex adaptive systems? If they exhibit 4 different characteristics. They're made up of self-similar parts. The cells in a mouse are the same as the cells, well, not the same, but they're more or less the same as the cells in an elephant, or in a blue whale, or in me, right? The roads in one city are the same as the roads in another city, composed of these self-similar parts. They're self-organized, so there is no orchestrator that creates me as a complex adaptive system. I self-organize into me over a number of years. They're complex, so the whole is greater than the sum of the parts. The way I'd like to describe this is if you took James and you put James into a blender, and then you poured James into a James-shaped mold, you wouldn't have James, right? You'd just have like James soup or something. It wouldn't be James, right? There's something additionally complex about me that makes me me, rather than just the components, just the sum of the components that make me up. And then you have this idea of emergent behavior. So if you run the same sort of experiment twice with a complex adaptive system, you'll often get different results. You can't tell the outputs from necessarily the inputs. And further to that, this idea of sublinear scaling or economies of scale, that can be traced back to a further 3 simple principles. The first is the idea of space-filling fractal networks. Now, you look at cities, you look at organizations, you look at us, probably quite obvious what these networks might be. In us, it's our circulatory system and our nervous system and so on. In cities, it's things like the road networks, it's things like the pipes that carry water into our houses and so on. And in companies, it's the way information flows through an organization, from the most information to the least and so on. Then you have this idea of invariant terminating units. So in mammals, the invariant terminating unit is a cell. In companies, it's someone doing work. In cities, it's houses. That's how it's defined. But this idea of is invariant terminating units that are self-similar to one another when you look at it from a certain perspective. I've been trying to get Thoughtworks to start calling us consultants. This, I think it's better than meat bags. I'd prefer to be a self-terminating unit than that, but invariant terminating unit, but never mind. And then the third principle is optimization, the idea that these systems over time optimize themselves. So for biology, that's evolution over geological time. For companies and cities, that's market forces generally. But some feedback loops that are optimizing the evolution of these complex adaptive systems. And as I say, they're everywhere. Right? Patterns can be described using these three simple principles. But the key thing is that hierarchical fractal networks, so much like the ones that exist in us, in our circulatory system, every time you see a hierarchy, mathematically, the scaling law that applies will be economies of scale. When you have hierarchies, you get economies of scale. It's as simple as that. It's just maths. Right? So mammals have our circulatory system, which is a hierarchical network starting at our heart, terminating essentially at the cells, and then that's the arteries and capillaries, and then our venous system brings the blood back to the heart. In cities, the hierarchies are the roads and the water networks and things like that. And in companies, the hierarchies are the hierarchies of information flow that we build in the organization. And essentially, Walmart and a convenience store, they're just the same. A mouse and an elephant is the same. It's just about the scale that they operate at. So, corporate metabolism. Why does revenue growth slow as size increase, according to this graph? There's someone taking a photo there. I'll go back. Why does revenue growth slow as size increase? Why do metabolic rates slow as size increases? It's literally down to the depth of the hierarchy. As you add depth into a hierarchy, things slow down. That's just what happens, essentially, right? So a mouse with only, I think the Etruscan shrew is the smallest mammal, and that only has like a heart and then one or two layers of arteries until it's capillaries and cells absorbing nutrients from the capillaries. Whereas the blue whale has many layers or many nodes, if you like, and branches in its circulatory system. So the heart is a long way away from the capillaries in terms of the network. And that's mathematically why blue whales have this much lower metabolic rate. They live a very long time, but they have a very slow metabolic rate. Same with elephants. They've got very long distance between heart and capillaries. Whereas mice, running around really fast, they've got a really shallow hierarchy in their circulatory system. And it's as simple as that. The deeper the hierarchy, the slower things go. And this is true not just for mammals, it's true for cities, it's true for companies, it's true for the way information flows through our corporate networks, and it's true for how water flows through the pipes in a city from reservoir into the city centre. So essentially what I'm saying is bigger animals are more efficient. Yeah, they've got a slower metabolic rate, they make better use of that by slowing down. And this is down to the depth of the hierarchy, and it's driven by feedback from evolution. Similarly, companies are more efficient because they develop these deeper hierarchies driven by feedback from market forces, and both slow down as they age. And I showed you that value stream map right at the start. That was a company that's about nearly 200 years old. Over that time, they've just built up process. They've developed this incredibly deep hierarchy, if you like, of information flow, where that value stream is one slice through the corporate informational hierarchy. That's one way of getting from work out the door. This value stream map, which takes months and months, which is built up over time. Everything takes a long time to do because it's an old organization. And one of the reasons behind this is we end up with things like queues in our system. Every time you look at Jira, essentially you're looking at a queue of work, but there are other queues. There are queues of decisions waiting to be made by architecture review boards. There are queues of decisions being made by change request boards. There's the annual budget cycle, which has a delay imposed of a year or so, depending, on average half a year, depending on when you want to get a decision made. And all these queues add overhead. Essentially, these queues, it's kind of like deliberately blocking your arteries. If you think about the flow of blood through your circulatory system, we get plaque buildup, essentially, and back pressure, which puts pressure on the heart and gives us heart attacks. When we add queues into our systems, queues into our information flow, we're doing the same thing. It's basically plaque buildup in the informational hierarchy of our organisations. And we don't really want that. That's kind of, it leads to the same thing as it leads to in us, which is bad outcomes. So I mentioned about, how long does stuff take? 5 manual testing stages taking months. Lots of different queues. And I like this book, which is my favourite book about queuing theory, really, and about the economics of what we do, principles, product development flow. And in Principles of Product Development Flow, he talks, Don Reinertsen talks an awful lot about the effect of queues on systems. And I've sort of started to think of these queues and putting blockages in as this idea of cholesterol building up over time in our informational arteries. So, corporate metabolism. As companies scale, they add more processes and hierarchy. Therefore, things slow down. But we also deliberately block our corporate arteries. I've mentioned a few of these deliberate blockages a minute ago. So here's a sidebar. Can we identify signs of aging? And I think we can in our organisation. I think we can do it in a similar way we do when we go to the doctor. Now, in the brilliant book, another canonical, immediate classic, Accelerate, which summarises the state of DevOps report over the years, they talk about a number of these factors that we can use to actually check whether organisations are healthy or not. I'll come to that in a sec. But fun fact, in Accelerate, they point out that change request boards or architecture review boards, they essentially predict, and I'm using that word advisedly, they predict low organisational performance. If you have a change request board or an architecture review board, the prediction is you'll be in the low-performing set of organisations in the study. All right? Again, and it's because it's like deliberately blocking the information flow in our corporate information hierarchies when you add these things. So can we understand how healthy we are? And I think, again, from Accelerate, we can take the 4 key metrics, which there's a lot of people have been talking about recently, about mean time to recovery, cycle time, change failure rate, and number of deploys per unit time. These 4 metrics, I think they're the equivalent of sort of taking your pulse or your blood pressure when you go to the doctor. It'll tell you whether you're healthy or not, more or less. It won't tell you why you're unhealthy, but it might give you a sign that you might need to do a bit more investigation. And you can monitor these things over time and see that when you start running 10Ks all the time, your metrics get better. Or when you start deploying more frequently and doing more automated testing, then your change failure rate gets better. So we can identify the signs of aging using the 4 key metrics. They're leading indicators, if you like, of organizational health in the same way that going to the doctor and having our blood pressure, temperature, heart rate and so on are leading indicators of our health. Now, and we can work to improve those. I've mentioned at the time that I mentioned earlier on Daniel Tuchel's North idea of safely and sustainably reducing the lead time to thank you. As teams, we can use these metrics and work towards improving them. But, and this is the big but, if you're in a hierarchy, an informational hierarchy, if you've got these very long value streams, if you're in a hierarchical organization, you can only improve them to the limit of the hierarchy itself. And that's maths. When you have hierarchies, they impose a limit on how much better you can get. Unfortunately, companies also die, much like mammals. And why is this? Why is it? It's a 50%. The half-life of a company on the exchanges is 10 years, 10 and a half years. 50% churn every 10 years. Companies die all the time. They get taken over. They get bust. They just cease to exist in some form or another. And why is it that happens? Well, it seems that, and there's a lot less research on this, but it seems that as organizations get older and as they get bigger, they sort of have this flip in mode where they stop doing the stuff that made them successful necessarily over time. When they were small and successfully building new products and selling new products and doing R&D and new product development and so on, and they flip into this self-sustaining mode where they're not concentrating on the stuff that made them great to start with, and in fact, instead they flip to just sustaining themselves. Right? So spending money on just being themselves rather than spending money on R&D and so on. And it's the same with mammals as mammals get older. There's a point at which we're using more and more of the calories that we're taking in as humans actually to repair damage internally than we are to doing things like being able to put new muscle on or et cetera, et cetera. So as companies get older, the same thing happens to them as happens to mammals when they get older. They slow down, and eventually, like mammals, they die. But they also, as they get older, tend to add more and more processes and constraints. And these are all for purely logical reasons. Why do we need a 6-week regression testing phase just to change a GIF on the website? Well, do you remember in 1994 when someone changed a GIF on the early website and it caused the site to go down on Black Friday and there was a thing and everyone got fired? So now we have 6 weeks of regression 15 years later. But which is all perfectly logical at the time. But over time, these processes, constraints, they build up until we have these really deep organizational hierarchies of information flow. So hierarchies grow and grow. And for hierarchies, they gain economies of scale for infrastructure. So our CFOs are right in the sense that as you double the size of an office, they get cheaper. The office gets cheaper. You don't need double the amount of network cables, et cetera, et cetera, et cetera. You gain economies of scale for infrastructure. But you achieve sublinear revenue growth as you scale. And finally, they reduce their metabolic rate over time. They're spending so much of their calorific intake, if you like, on sustaining themselves that eventually they just grow old and die. But fortunately, there is something we can do about this. There's another type of scaling law called returns to scale. And cities exhibit both of these types of scaling law. So as a city doubles in size, socioeconomic factors increase by more than double. So the amount of innovation, wage growth, number of professionals, the amount of crime, disease and pollution is all more than double as you double the size of a city. So what they end up with in cities is economies of scale for infrastructure and returns to scale for socioeconomic factors. And this is why cities are so successful. And also, incidentally, as you double the size of a city, people do actually walk faster. There was some research done on mobile phone data by MIT, and it's actually true, up to the limit of how fast your legs will go. Anyway. Why is it that cities exhibit these effects? Well, it's because there's a different type of fractal network that's going on in the city for socioeconomic factors. There's a different type of fractal space filling network called a small world network. We're familiar with these from social media, from our groups of family and friends. These are social networks. They're also fractal space filling networks, but they're social networks. And also, there's been a lot of research recently into, or in the past, into the groupings by which people have the most, empathy with one another. This is done by a guy called a sociologist called Dunbar, and these are Dunbar's numbers. You might have come across 150 or 200 as one of Dunbar's numbers. There are other Dunbar's numbers. So they scale up from 5, which is your nuclear family, if you like, through 15, which is your extended family, through your close friends, through acquaintances, and so on. And this is why certain organizations choose to operate and choose to scale themselves around particular numbers, because at 150 or 200 people, that sort of scale means I personally will know everyone, or at least be able to have a conversation and know that Kate likes playing golf, for example, but Paul likes playing Baldur's Gate 3, and I can talk to Paul about Baldur's Gate 3, I can talk to Kate about golf or not, I know nothing about golf, but at least I have some social connection. As you scale beyond that, beyond these sizes of groups, then it starts to become anonymous. You just physically as humans, we can't hold information about more than about 200 people at some surface level in our heads at once. And so this idea of 2 pizza teams, this idea of scaling via team topologies, value stream aligned teams built around these small numbers, Dunbar's numbers, 15 is almost like an XP size team, if you like, extreme programming size team, maybe a bit smaller. Scaling around these small teams has led to success in many organizations. And actually this is what drives these socioeconomic returns to scale in cities. So just to drive that home, just to ram it home, economies of scale are due to hierarchies, returns to scale are due to social networks. And the reason, much like you can maybe put AWS on the top here, the reason that leads to these things is because you can just bolt these small teams on next to one another, decoupled and cohesive in and of themselves, in the same way that cities grow by building new suburbs and expanding outwards without impacting the internals of the city itself. So as cities grow, they gain economies of scale for infrastructure, returns to scale for socioeconomic factors. They rarely die, and they gain 115% of the stuff for 85% of the cost. Now, I mentioned other organizations that are sort of using some of these ideas. Are there organizations using these ideas? Well, actually, I work for Thoughtworks, and we grew this way. It's not so, I think it's not quite so true now, but we grew using by scaling via social networks and Dunbar's number. We have an incredibly flat hierarchy, and we would open a new office rather than scale beyond about 200 people in an office. So we had multiple offices in Bangalore, for example, in Bengaluru. We opened more offices in India rather than concentrate everyone in one particular city. We're in, 8 tier 2 cities in China for the same reason. Because we want to be able to, we want to scale by Dunbar's number, which means that people know each other. This is how you retain culture. This is how you retain a sense of purpose. Spotify, you could argue the Spotify model is a classic example of describing how to scale via social networks. Squads, which are chapters which are composed of smaller subunits, all of which are decoupled from one another, ideally. I don't know, it's not exactly true, but it's an example of trying to scale using social network growth rather than scale via hierarchy. Valve, famously, they leaked the handbook some years ago, and they actually had the small world network in it and said, this is how we want to grow. They actually said, we want to grow via small world network growth. And finally, back to Amazon. And this interesting number of 1.15. So this is the 115% that you get when you are scaling via social network growth. Right. So, going back to what that person at the event I was at said, as we get bigger, it's easier for us to get bigger. It seems to be the case. And there seem to be this set of underlying principles pointing to why, which is scaling via social networks, scaling via small teams that are decoupled from one another and cohesive, building software in a software architecture that is also cohesive and decoupled. And using these ideas from things like team topologies to describe that. So as most companies get bigger, it gets harder to get bigger, but as Amazon gets bigger, it's easier for them to get bigger. And as I say, if you haven't come across this book yet, this is a strong recommendation from me to go out and take a look at it, because it's fantastic. It goes into an awful lot more other than just the team shapes. It talks about how you can decide about how to split teams, how the substructures work, how to think about things like cognitive dissonance and how much software our engineers have to look after at once. Really interesting ideas that we can use in everyday practical ways in order to structure our teams and organizations. So I'm going to sum up software architecture, team topologies, and complexity science. This is, as I say, this has been quite a journey for me over the last however many years, getting deeply into complexity and getting deeply into understanding how work flows, how work works, which is another talk I'm doing tomorrow, and being based on the underlying principles, I think, microservices being based on this set of underlying principles, which is the reason we decentralize, the reason we create these small teams that are autonomous as far as they can be, that have the right amount of information and push decision-making to those teams, is so that we can take advantage of these really strong connections we get from using things like Dunbar's number and scaling around small world networks, social networks. And team topologies, just read it, it's awesome. Finally, hierarchies, slow metabolic rates. Think about team shapes for flow and this idea of forcing functions for flow. That I mentioned back at the start in Jeff Bezos' memo, the forcing functions for flow, I've called it. Now, you might have heard the phrase, it's not paranoia if they are really out to get you. You've come across that idea, you're not paranoid if they are actually out to get you. Would it surprise you to know that Jeff Bezos lives about 10 miles from the Santa Fe Institute in Santa Fe, where that's his main property in New Mexico. And in fact, he's the main sponsor for a lot of the work that goes on there, or he's a sponsor for a lot of the work that goes on there. Interestingly, he's known this for a long time. I don't know for certain, but I think those forcing functions are a sign that he's deliberately guided Amazon in this direction, or certainly AWS, in this direction of small world network growth, which is fascinating and scary. These are the references from this. Obviously, this talk will be online. There's a bunch of awesome books. There's the original papers as well that I've referenced in it. Yeah, and that's me. Thank you very much.